Chemists, in the last lesson we looked at using organometallic reagents as carbon nucleophiles to primarily make alcohols. So let's say I wanted to make this alcohol here, it's secondary. You could imagine going backwards and bringing in an aldehyde that already has a benzene attached. And in this case, just a one carbon organometallic, for example, methyl grignard, CH3 MgBr, followed by an aqueous workup. What would that look like? Well, the grignard would attack the carbonyl carbon, the electrons would go up, you would add that one new carbon, and you'd get the secondary alcohol after protonation of that O negative. Alternatively, you could come at this from the other direction and imagine bringing in the organometallic as that phenyl group. So I could have, let's say, phenyl grignard, or the lithiate, and that would bring in this piece, which means I would need an aldehyde that contains the rest of this, so a 2-carbon aldehyde. And that would mean I'm reacting this grignard with a 2-carbon aldehyde like so. That's acetaldehyde, followed by an H+ step. So anytime we look at an alcohol, we find the alcohol carbon, and whatever's directly attached to that, you could imagine bringing in as an organometallic, and the rest of it was along for the ride. The first example had us bring in a 1-carbon piece to make that methyl attached there. The second one we just showed had us bring in the phenyl group. Now, you'll also notice in this particular alcohol, well, there's a third bond there, isn't there? There's a hydrogen. Unfortunately, there's no such thing as a hydride grignard. It's not organometallic. But is there a way we could bring in a hydrogen as a nucleophile? Yes, there is. That's the point of what we're going to look at today. This is called a reduction. And there are special reducing agents that work as H anions to attack carbonyls. So if we have something like a ketone, we can get a secondary alcohol by reacting it with a source of hydride. I just have it in pair brackets to indicate that. There's 2 reagents that we use for this more often than others. They are sodium borohydride, which has the formula NaBH4. And just to show you what it looks like, it's a sodium cation and a borohydride anion. That's a boron with 4 bonds and a negative charge, formal charge on the boron atom. It acts as H-. Just like organometallics behave like carbon anions, these reagents behave as a source of hydride, a hydrogen with its anion. And make a note that sodium borohydride only reduces aldehydes and ketones. It's not reactive enough to hit other carbonyls, so things like esters, acid chlorides, well, for the most part esters and other things, we will see that there's other ways to reduce those. Namely, it's the other reagent right next to it, lithium aluminum hydride. Lithium aluminum hydride is very similar. It's an alkali metal lithium, aluminum, and then 4 H's. It's got almost a mirroring formula. The structure is a lithium cation, and then an aluminum hydride anion with a negative charge on the aluminum. This also acts as a source of H-. Acts as H-. Now, unlike sodium borohydride, which only reduces aldehydes and ketones, for now, this reduces everything. So I'm just going to say, if you see anything that is reducible, LiAlH4 reduces everything. Sometimes it's abbreviated as lithium aluminum hydride, LAH. In fact, chemists will even say LAH to just mean the acronym lithium aluminum hydride. So let's just look at some examples and see if we can figure out what molecules we would get from these reducing agents plus aldehydes, ketones, and a few others. The left-hand column, I've got all sodium borohydride, and the right-hand lithium aluminum hydride. Sometimes it'll be the same, sometimes it'll be different. The first one is an aldehyde. If you're having trouble remembering your functional groups, go ahead and label them as you see them until you get really comfortable with seeing them. So NaBH4 acts as a hydride, and it will react with an aldehyde. Draw an arrow from the H- and send that carbonyl carbon up. get all 5 of the carbons you used to have, an oxygen anion. Just for completeness, I'll show there was that H that used to be there, that's still there from the aldehyde, and then there's a new one. And that's what this does. And then as we saw with organometallics, there's an aqueous workup. So that oxygen anion sees the H+, and you get an alcohol. In this case, a primary alcohol. Right next to it, we get lithium aluminum hydride. It acts exactly the same. It does exactly the same thing. I'm going to show the mechanism. You add an H to both the carbon and the oxygen. Pi bond is gone. So there's no difference between LaH and sodium borohydride, the reduction of an aldehyde. Same kind of thing happens with a ketone. I have cyclohexanone. I'm not even going to draw the arrows. I'm just going to think them in my head that this is attacking that carbonyl, sending those electrons up. So you will turn cyclohexanone into cyclohexanol. In fact, right next to it, I'll just go to the right. Same thing. LaH also reacts with ketones. So for aldehydes and ketones, these reagents are interchangeable. What about down below this? Here we have a ketone and an aldehyde. Let's assume it reacts with both. Well, that would turn the ketone into a secondary alcohol and the aldehyde into a primary alcohol. And then right next to it, same thing. I still have yet to see an example that distinguishes one of these reagents from the other. And then I get to the next one. Aha, now we are not in aldehyde and ketone territory. This is an ester. Esters with NABH4, no reaction. However, esters will react with LaH because LaH essentially reduces everything. Let's figure out what it would look like. LaH acts as H-. It'll attack the carbonyl carbon, and the electrons will go up to the electronegative oxygen. You'll get an anion, a new H, and the methoxy. That was the long for the ride. Now think back to what organometallics did to things like esters. Here we saw the oxygen reform the carbonyl and kick out the alkoxide. This is what makes esters and acid chlorides, and actually a whole other class of carbonyl-containing compounds, different from aldehydes and ketones. They still undergo additions, but they'll undergo over-addition. So you get an intermediate that looks just like an aldehyde, where I kicked out methoxide. So LaH will react with this again. You get over-addition, which, if it acts as an H-, it attacks that carbonyl that's reformed, and I get 2 new H's on what used to be my aldehyde carbon. So then once both of those things see H+ in your aqueous workup, you'll get a primary alcohol and then a second alcohol from whatever used to be attached to the ester. So esters undergo this over-addition of LaH, and they don't react with NABH4 at all. So those two are very different than the other two. Knowing that, see if you can predict what you would get from this last example in this sequence. Here we have a cyclic ester and then a tethered aldehyde hanging off of the ring. What would you get if this molecule reacts with sodium borohydride? And then what would you get if the same molecule were to react with lithium aluminum hydride? Try that now, come back and check and see how you did. Okay, so for that NABH4 reaction, well, it doesn't react with the ester, so that will stay put. The aldehyde will give me a primary alcohol. So hopefully you drew the cyclic ester, which is called a lactone, exactly the same, and your aldehyde became a primary alcohol. What about with LaH? Well, the aldehyde functional group is going to also turn into a primary alcohol. But what about this ester? Let's see if we can model that off the one that's right above it. Right above it, it looks like overall, I essentially carved off that methoxy group. I got a primary alcohol where the carbonyl used to be, and then another alcohol on the other side of the same molecule. That's what I ended up getting in the end. So that's what I'm going to get with this ester. And I'll try to show myself a little bit about that without drawing the whole mechanism. You will cut that carbon-oxygen bond. This will become an alcohol from the actual reduction, and this will also become an alcohol just from the protonation at the end of the step. In fact, this will become an alcohol because it's just an aldehyde, and that reacts with LAH just as if it was NABH4. So I'm going to have 3 alcohols in this molecule, and all the carbons are right where they were. So I'm going to draw all the carbons first. I've got this open-ended ring with that carbon up there. That oxygen now becomes an alcohol. That, what used to be my ester carbonyl, becomes a primary alcohol, and this, what used to be my aldehyde carbonyl, becomes another primary alcohol. So there's my carbon chain, and there it still is in the product. Okay, so let's apply this to a quick synthesis and combine it with just some other reactions, and we'll see how we use these to make molecules turn into different molecules. First up, ozonolysis. That will cut the carbon-carbon bond that's got an alkene. You'll get 2 aldehydes. The ester is along for the ride. So I have an open 6-membered ring. I have an ethyl ester along for the ride. And then I have 2 aldehydes, each coming off of the carbons that used to be the alkene carbons. Sodium borohydride will reduce both of those to primary alcohols. In my head, I'm picturing hydrogen with negative charges attacking those carbonyls. What about the ester? Doesn't react with sodium borohydride, so along for the ride. Then, 2 equivalents of NaH and 2 equivalents of bromomethane. This is the Williamson ether synthesis, which we saw 2 lessons ago. It takes alcohols, it does an acid base with NaH, so you get oxygen anions, and then each of those will do an SN2 on bromomethane, so I turn both of those OHs into O-methyls. So I draw everything the same and only change what's changed. And there's this double ether tethered to this thing that used to be an ester. And then lastly, we have ethyl Grignard. So this is from our previous lesson. To help me figure out what this does, I'm going to draw out the ester. This is an abbreviated ester, CO2ET. What does that actually look like? It's a carbonyl with an oxygen and an ethyl attached to that oxygen. So the ester reacts with ethyl Grignard. It reacts twice. It behaves like ethyl anion. And if it helps to remember that for now, you can sort of draw it like that. And it will attack the ester 2 times, times 2. So I get a tertiary alcohol at the top of what used to be this 6-membered ring. I have a lot of stuff along for this ride. Ethers are very unreactive. That's why we see them as solvents so often. So those methyl ethers are just along for the ride. But my ethyl ester is now a tertiary alcohol where I have 2 new carbon groups attached to it. And if I really want to be complete, what happened to the ethoxy that got kicked out? Well, it found an H from the acidic hydrolysis, so you also have ethanol, but it's such a small molecule compared to the other one. It's okay if you don't draw it. And for fun, it looks like they gave me the name of this molecule. This is 3-ethyl-7-methoxy-4, 2-methoxy-ethyl heptanthreol. You could go ahead and confirm that that name actually matches the molecule that we see here. Okay, so that's just meant to show you how we can use reducing agents, sources of hydride, to attack mostly carbonyl compounds to make alcohols.